For centuries, humanity has asked one question that defines the very essence of existence. What is time? We measure it. We feel it passing. But do we really understand what it is? Now imagine this. You're sitting inside a spaceship that's about to travel at the speed of light. You look at your watch. The second hand begins to move slower and slower until suddenly it stops. Everything around you freezes in time. Outside, millions of years might pass, but for you, not even a single second. How can that be possible? How can time itself stop? To answer that, we have to dive into the mind of a man who reshaped our understanding of the universe, Albert Einstein. Before Einstein, most scientists saw time as something absolute, a universal clock that ticked the same for everyone everywhere. That was the world according to Isaac Newton. In Newton's universe, time flowed evenly, unaffected by motion or gravity. But in 1905, Einstein shattered that belief. He introduced the theory of special relativity, and with it, a new vision of the cosmos, one where space and time are not separate but part of a single, an entity called spacetime. Einstein's idea was simple but revolutionary. The speed of light is the same for everyone, no matter how fast they move. Whether you're standing still or flying in a rocket, if you measure light, you'll always get the same result. 299,792 kilometers per second. But this constant speed comes with a cost. To preserve the speed of light, space and time themselves must adjust. That means if you move faster through space, you must move slower through time. Think of the universe as a cosmic fabric, space-time. Every object that moves through this fabric follows a kind of cosmic rule. The combined speed through space and time is always constant. If you're sitting still, you're moving through time at full speed, second by second, moment by moment. But if you start moving faster through space, you must spend less on time to keep the balance. At the speed of light, all of your motion is through space, and none is left for time. So for light, time stops completely. From a photon's point of view, it leaves a distant star and reaches your eyes in no time at all. Even if the journey takes billions of years from our perspective. In 1971, scientists performed an experiment known as the Haffel-Keating experiment. They flew atomic clocks around the Earth on commercial airliners, one eastward, one westward, and compared them with identical clocks left on the ground. The result? The moving clocks ticked slightly slower than the stationary ones. Just as Einstein predicted. On a larger scale, astronauts aboard the International Space Station also experienced time dilation. Traveling at nearly 28,000 kilometers per hour, they age about 0.01 seconds less per year than people on Earth. It sounds small, but it's proof that time is not absolute. It bends, stretches, and slows with motion. Now let's imagine the ultimate limit, traveling at the speed of light. What would you experience if you could move like a photon? For light, there's no time between emission and absorption. A beam of light, leaving the sun and reaching Earth in 8 minutes, from the light's perspective, happens instantly. The beginning and the end of its journey are one and the same. For a photon, the entire universe exists in a single frozen moment. But for us, bound by the limits of mass, such speed is impossible. And that brings us to another question. Why can't anything with mass reach the speed of light? Einstein's other famous equation, E equals mc, tells us that energy and mass are two sides of the same coin. As you move faster, your kinetic energy increases, and so does your relativistic mass. The closer you get to light speed, the more energy you need to keep accelerating. And at the speed of light, you'd need infinite energy. That's why only light itself, which has no rest mass, can travel at that ultimate speed. For everything else, it's a physical barrier that can never be broken. What does time stopping really mean? When we say time stops at the speed of light, it doesn't mean the universe literally freezes in place. It means that from the light's own frame of reference, time has no meaning. There's no before or after, only now. But from our point of view, the light is still moving through space and taking time to get where it's going. That's the beauty of relativity. Reality depends on who's observing it. For the photon, time doesn't pass. For us, it takes billions of years to cross galaxies. Both are true in their own frames of reference. So if time slows down as we approach the speed of light, what happens if we try to go beyond it? Could we move faster than light? And if we did, would time start to move backward? It's a question that has fascinated physicists, philosophers, and dreamers alike. But before we go there, we must first understand what happens near the edge of light speed. As you accelerate closer and closer to the speed of light, strange things begin to happen. Distances shrink, time stretches. The universe in front of you starts to flatten, and all directions seem to collapse into one single beam of light. This isn't imagination, it's the direct consequence of Lorentz contraction. Another part of Einstein's equations. The faster you go, the more space compresses in the direction of motion. From your perspective, the distance to your destination becomes shorter and shorter, but the time it takes to get there also slows down. At 99.99% the speed of light, a journey to the nearest star, which would normally take for years, could seem to pass in a matter of days, but for people on Earth, for years still go by. Time itself has become relative, not universal. To you, time has slowed down. To them, it has not. That's the strange beauty of relativity. Everyone's version of reality is equally true. Physicists call the speed of light the ultimate speed limit of the universe, not just because it's fast, but because it defines the structure of reality itself. At that speed, the relationship between space and time becomes so distorted that they can no longer function. In the way we understand them, imagine space and time as coordinates on a grid. The faster you move, the more those coordinates twist and warp. At the speed of light, that grid collapses, time becomes meaningless, and space has no distance left. Everything merges into a single point. That's why for light, the entire history of the universe is one eternal now. It's almost poetic, the light from the Big Bang, still traveling through space, is frozen in its own existence, forever unchanged since the dawn of time. But what if somehow we could cross that boundary? What lies on the other side of light speed? Mathematically, if an object could travel faster than light, the equations of relativity predict something shocking. Time would run backward. That means from our perspective, such an object would be moving not just through space, but also backwards through time. Cause and effect would reverse. An effect could happen before its cause. It sounds impossible, and for now, it is. But in the realm of theoretical physics, it opens doors to ideas that challenge our deepest understanding of the cosmos. According to theory, tachyons could never slow down to or below the speed of light, just as we can never reach it. For them, faster than light is the natural state of being. If tachyons exist, they would experience time completely differently from us. To them, everything we see as the future would already have happened. They would, in a sense, live in a reverse timeline. So, does that mean time travel could be possible? Maybe, but reality seems to have built-in protections. Barriers that keep causality intact. No experiment has ever detected a tachyon, and modern physics leans toward the idea that they don't exist. But light speed isn't the only thing that can stop time. There's another gravity. Einstein's later work, general relativity, showed that massive objects like stars and black holes can also warp spacetime. The stronger the gravity, the slower time passes. Near a black hole, where gravity becomes nearly infinite, time nearly stops, just like at light speed. In 2014, the movie Interstellar depicted this idea beautifully. Astronauts visiting a planet near a massive black hole experienced time so slowly that 1 hour for them equaled 7 years on Earth. That scene wasn't science fiction, it was based on real physics. In fact, around the event horizon of a black hole, time dilation becomes so extreme that from an outside observer's point of view, anything falling into it appears frozen in time. So whether it's motion or gravity, both can stretch or stop time because both distort space-time itself. All of this brings us back to a bigger question. If time can slow, stop, or even reverse what is time really. Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." To him and to modern physics, time isn't something that flows. It's another dimension, much like space. In the block universe theory, the past, present, and future all exist simultaneously, like pages in a book. We are simply reading those pages one by one, in sequence, but the book itself is already complete. Light, on the other hand, doesn't move through those pages. It exists on all of them at once. That's why, from the perspective of light, time doesn't move because light is beyond the flow of time altogether. Now, while these ideas sound vast and cosmic, they also reveal something deeply personal. Think about it. Every moment we experience, every heartbeat, every second we count is defined by the rhythm of time. But the universe itself doesn't care about our seconds or minutes. Time bends, warps, and stretches depending on where we are and how fast we move. We live inside a reality where now isn't universal, it's personal. Your now and mine aren't the same in the grand scheme of spacetime. That realization changes how we see everything, from the movement of galaxies to the meaning of life itself. If light experiences no time, then what about the universe made of light? Stars emit light that travels across billions of years, yet from the light's point of view, that journey happens instantly. That means much of the universe we see, the distant galaxies, the ancient starlight, all exist for us as a delayed illusion. We're looking at the past, always. Even the sunlight on your face is 8 minutes old. So when we gaze into the cosmos, we're not just seeing across distance, we're seeing across time. And the deeper we look, the closer we come to the beginning of everything. Does time really exist? Modern quantum physics adds another twist. At the smallest scales, the realm of particles, time behaves strangely. Some interpretations of quantum mechanics suggest that time might emerge from interactions, rather than being fundamental. In other words, time might not exist at all. It could be a property that appears only when energy and matter interact. That idea challenges everything we know about reality. It means that time could be an illusion, a tool created by our minds to make sense of motion and change. But even if that's true, it doesn't make time any less meaningful to us. Because in our world, the human world, time defines love, loss, growth, and life itself. At the end of the day, light speed remains the ultimate boundary, the line between existence within time and existence beyond it. It separates the universe of motion and life from the timeless domain of light. Every law of physics, every experiment, and every piece of evidence we have says the same thing. Nothing with mass can reach the speed of light. Because if we could, time as we know it would cease to exist, and maybe that's the universe's greatest safeguard. Because without time, there's no cause, no effect, no experience, and no meaning. Einstein didn't just explain the universe, he redefined it. He showed that reality is not made of things, but of relationships between space, time, energy, and matter. His work didn't just tell us that time slows down at high speed. It told us that the universe itself is flexible, dynamic, and interconnected. That everything from the smallest atom to the farthest galaxy dances to the same cosmic rhythm, the rhythm of space-time. And in that rhythm, light plays the eternal note, timeless, ageless, infinite. So why does time stop at the speed of light? Because light doesn't move through time the way we do. It is time's boundary, the edge where motion, energy, and existence meet. For light, there is no journey, only presence. For us, bound by matter and gravity, time continues to flow, second by second, heartbeat by heartbeat. But every photon, every beam of starlight that touches your eyes, is a messenger from that timeless realm. It carries the memory of the universe's birth, frozen in eternity. Whispering the same truth Einstein discovered over a century ago, time doesn't rule the universe. The universe creates time. And maybe, just maybe, when we finally understand light, we'll understand time itself.